So welcome back. This video is going to talk about applying the migration model to different situations. So in my previous video, what we went over was we're going to assume that customers are in some state in each time period. So the absolute simplest case is what I call the buy-no-buy model, where at any given point in time, the customer has either bought from you in this month, say, or did not buy from you in this month. And then what happens between the months is that they will transition between these two states. So with probability P1, a buyer buys again. With probability 1 minus P1, a buyer decides not to buy in the next month or period, whatever the period is. Likewise, a customer who has not bought buys again with probability P0, or decides to remain a non-buyer with probability 1 minus P0. What we showed is that we can work out the customer equity of such a system. If we start out with n customers, so this is a vector giving the number of customers that we start out with in each state, we multiply that by this thing in the middle, which is basically the transition matrix discounted, and then we take the inverse, and this is the value vector. So I'd like to talk about maybe 3 settings in this video where this could get used, and then in the next video we'll talk about 2 more. So the first situation that I want to talk about is the simple retention model. So we spent a whole lot of time talking about how to handle contractual situations where the customer signs up and sends money until the customer decides not to. What we can see is that the simple retention model can be written as a buy no buy model. So this is what it would look like. You could think of, here I'm buy, here I am no buy. And if we use the notation that we used back in the simple retention model, with probability R, the customer gets retained. So I send Netflix money this month. With probability R, I will stay around and send Netflix money next month. But then with probability 1 minus R, I decide to cancel, and then with the simple retention model, we assume the customer never comes back. So how do I capture that notion that the customer never comes back? Well, I make this state an absorbing state. So absorbing means that once I enter the state, I can never leave. So I have probability 1 of remaining in the no-buy state. That's the simple retention model. Notice that the path that we had before has probability 0. So that's our simple retention model. What's kind of an interesting exercise is to write out the transition matrix for the simple retention model. You can easily invert a 2x2 matrix in closed form and then work it out. Your value vector looks something like this. The value vector, if I'm in the no buy state, you get $0 from me. If I'm in the buy state, you get M dollars from me. So work out this expression, and what you're going to see is that you get exactly the same formula that we had back when we worked out the simple retention model using some messy algebra. Just point out another thing. You may have been a little bit concerned about this assumption that once I have left Netflix, I will never come back. Once I leave my cell phone carrier, I never come back. It's probably not very realistic because, in the case of cell phones, if I go to another carrier, chances are that other carrier is going to be just as bad as my current one, and I may be coming back after a while. So if you don't want to assume this gone for good assumption that I will never come back once I'm in the no-buy state, what do? Well, you use the buy-no-buy model. So you can see where by allowing non-zero probability of coming back from the non-buy state generalizes the simple retention model. So if you're uncomfortable with this assumption, we can easily relax it with the migration model. Well, what I thought I'd do next is walk us through a simple example. So let's say that we have the following setup. I have a database with 100 customers who are inactive currently, and then there's 200 customers that just bought from me. And so they are fully active. So here's the number in the buy state, the number in the non-buy state. Suppose that I market to everybody every month, and I spend $1 on marketing. Now, when a customer buys, I actually make $21, but if you take 20 minus 1, you're at $20. This would be the net contribution less marketing costs. We can think of that as being our V vector. And then here's my transition matrix. Let's just go draw that out so that we can see it. So here's my buy state. This is my no buy state. With probability 0.4, I buy again. And so that's what you're seeing right here. With probability 0.6, I go into the non-buy state. Now, non-buyers are a bit harder to activate, which is very realistic. So maybe there's only a 20% chance that a non-buyer comes back to buy from you again in the next period, while there's an 80% chance then that a non-buyer remains a non-buyer. The product of this, let's go do this live in R. And so I have just read in my P vector. If you're not convinced of this, let's go see it. So here we've got our P vector. Here's my N vector and my value vector. So N vector I called the initial vector. Here's the value vector. And if we want a two-step transition matrix, we'll just compute this product. So let's go do that. I think it's very important to interpret these numbers. So let's start with this one. What this says is, if I start out in the buy segment, there's a 28% chance that 2 periods from now, I'm in the buy statement again. It might help to go look at this diagram. If I start out in the buy statement, there's 2 ways for me to be in the buy statement 2 periods from now. I either buy and I buy again, or I don't buy the first period, but then come back to life in the second period. And so in this case, there's a 28% chance that someone who just bought buys 2 periods from now. There's only a 24% chance that someone who is in the non-buy state buys from us 2 periods from now. If I want the 4-step transition matrix, I would just multiply P2 by itself. And so what you're going to see is that probabilities are approaching some limit. That turns out to be the case. When we cover eigendecompositions a little bit later on, we're going to be able to prove that. So the next thing I'd like to do is to compute customer equity for this little toy example. What I need is the identity matrix minus P over the discount rate inverted. In R, you can make yourself an identity matrix just by saying diag. So diag2 would give you a 2 by 2 identity matrix. If I take diag2 minus P over 1.1, so 1.1 is 1 plus the discount rate, which was assumed to be 10% per period. So if you go back to the formula, what I need to do with this thing, I've just computed I minus that. I need to invert it. So in R, you can invert that with the solve command. Lifetime value is simply going to be solve times the value vector. What this says is a customer who starts out in the buy state has a lifetime value of $66, whereas a customer who's in the non-buy state is only worth about $40. That's including the transaction that occurs at time 0. And so this ought to make a lot of sense because remember, you make $20 for a buyer. So it's like you're getting an additional purchase because of what happens at time zero. You're getting a little bit more because those who are in the buy state have a higher chance of buying. And so that's why this isn't just $20. It's a little bit more than that because you're a little bit more likely to get some initial purchases. Whereas someone who starts out in the non-buy state is only worth about $40.33. To get to customer equity, we would multiply this by n. So we started out with 100 customers in the non-buy state, 200 in the buy state. So if I take 100 times 40, I get $4,000. And then if I take 200 times $66, well, the sum of those two gets me to about $17,000. So that's what this customer database is worth to us. I'd now like to cover another example. So about 15 years ago, I organized a lifetime value modeling competition. So we were working with a major U.S. nonprofit organization. So this could be something like Easter Seals or the Heart Association or the Paralyzed Veterans. They gave us the transaction and contact history for all donors up through about the beginning of 2008. We launched the contest in the beginning of 2008. The first task was to predict donations in this 2-year window from September 1st, 2006 through August 31st, 2008. So the fact that we launched this competition in the beginning of 2008 meant that nobody knew the right answer. Nobody knew how much those customers were going to donate in 2008 through the end of August. Now, there were actually 3 tasks. In addition to the customer equity task, which we're going to talk about here, there was also a task of predicting things for individual customers, as well as figuring out which customers would come back. We're only going to focus on task 1 in this video. So we attracted a very diverse set of participants from leading universities and consulting companies around the world. These companies used a lot of very fancy methodologies. What I thought was really interesting was nobody used one of these simple Markov chain models. The Markov chain model, by the way, was proposed by a friend of mine, Phil Pfeiffer, and his colleague Caraway back in 2000. So people knew of this method. Markov chains have been around for decades. Nobody tried it out. So this shows a time plot of the gift amounts across all these customers in this particular cohort. And we can see that it's very cyclical. It looks like people are very generous every December, and then they're not so generous in other time periods. So if you keep a running total, so you can think of this as like the amount that the time plot changes. This is like the differences. You know, how much more do you get each period? This graph shows the cumulative amount of revenue generated from this cohort of customers. And so what we see is you have every December you get a little bump. The slope increases a bit as reflected in this graph over here. Here's the real task. The task was predict how much you're going to make in the last 2 years. The correct answer was about $506,000 was the customer equity of that cohort that was acquired back in 2002. Now, I'd like to point out that if you took a ruler and laid that ruler down and extended it out 2 years, you wouldn't hit the number exactly, but you would come pretty close. Here are the results from all these famous professors and famous consulting firms. So remember, the correct answer was about $506,000, which is indicated by this red arrow. There were some entries that were way off. So I don't know how you could ever guess that that group would be worth a tiny amount or off by several orders of magnitude here. I think there's some really important lessons to be learned from this. Number one, make some simple graphs. This simple graph would get you really close to the right answer. Do that before you try any fancy deep learning neural network. I'm not sure why someone used a Kahuna neural network, but someone did. So start simple and then build up from that. So I was curious, what would happen if we used a Markov chain model? So let's take the database as of the end of the data that we gave the participants and use that to forecast what would happen in the next 2 years. So I'm going to go sketch out the Markov chain model that we used. I like to call this the recency model. So remember what I said earlier in a previous video. Recency is the time since the most recent donation or purchase if it's a retailer. The relationship between the probability of buying again and recency usually looks something like this. So if you have a customer who just donated to you, chances are they'll donate again with a pretty high probability. Alternatively, if you have a customer who donated to you, say, 4 years ago, the chance that that customer is going to donate again is substantially smaller, and that should make a lot of intuitive sense. So this is going to be my model. We're going to have a recency equal to 0, meaning donated in most recent year. Well, why don't I just write it out here? In the most recent year. Then we're going to have an R equal to 1, R equal to 2, and R greater than or equal to 3 state. So this is the way it will work. The probability that someone who just donated to you donates again to you next year, and you do this over years, we're going to call P naught. Now, what happens to a customer who decides not to donate? Well, there's only one place for that customer to go, and that is to the R equal to 1 segment, and that will happen with probability 1 minus P naught. Now, if I'm in 1 year lapsed, so the way to think about this is I'm trying to forecast what's going to happen in the next 2 years. This is year 1, year 2, year 3, year 4. So the people in this segment donated last somewhere in here. There were no donations in 1 year ago. So just call that now. So this group is 1 year inactive. So 1 year Well, suppose that these customers donate again with probability P1, and if they decide not to donate, they're going to lapse into being 2 years lapsed. So a 2 year lapsed customer last donated here. And so they didn't donate here, they didn't donate here, they made a donation, say, back here somewhere. Well, the probability that one of these customers comes back, we're going to say is P2. The probability that they lapse further is going to be 1 minus P2. Then the probability that one of these customers comes back to life, we're going to call P3, and the chance that they remain inactive will be 1 minus P3. So this is the state diagram for this recency model. So we could make ourselves a transition matrix that would look something like this. This is time t, and you can be in recency equal to 0, recency equal to 1, recency equal to 2, recency greater than or equal to 3. Here is time t plus 1. So this is r equal to 0, r equal to 1, r equal to 2, r greater than or equal to 3. So what we have here is P0, P1, P2, and P3. Now, if I'm in state R0, so I just donated to you, where do I go? Well, 1 minus P0, with probability 1 minus P0, I go here. Then those two can't happen. I think it's very clear when you look at the state diagram that if I'm in this state, there's two places I can go. Either I come back or I lapse. All right, well, what happens to these guys? Well, I can't remain in recency equal to 1. So if I'm 1 period lapsed, there's no way to remain 1 period lapsed. I either come back to life, which means I have recency 0, or I go to 2 period lapsed, 2 year lapsed. So 1 minus P1. Likewise, I can't jump directly from this state to this state. Well, what can happen to me if I'm in R equal to 2? Well, I either donate again, and I come back to being an active customer, or I lapse further. So probability 0, 1 minus P2. Finally, if I'm in this state, this is what my transition matrix is going to look like. Well, I set this up in R. Here are the customer counts, as well as the value vector. So let's go take a look at this. As of the end of the data, here are the number of customers I had in the recency equal 0 state, the recency equal 1, 2, and 3 plus. So you can see I have a whole lot of customers who are very inactive at this point. The average donation amount was $69. In this contest, we weren't accounting for marketing costs, so I don't need to worry about that. So I could compute the transition matrix, and here we have it. Let me point out how I did this. So where did these probabilities come from? Well, let's go back and look at my chart. You can see that the data started in 2002 and ended in 2006. So here's 02, 03, 04, 05, 06, 07, and 08. And the original task was to predict what was going to be happening out here. Well, I decided to turn the clock back, and I could observe purchases here and use recency as of this point to make that forecast of what's going to happen in this next period. Now, having computed those probabilities, I could then take the clock back forward and use that to forecast what would happen over the next 2 years. So let's go take a quick look at this. So what this says is if I'm in the recency equals 0 state, there's about a 57% chance that you're going to get me to buy again. If I'm 1 year lapsed, you'll see that probability gets cut a little bit more by half, so only a 25% chance. If I'm 2 years lapsed, there's about a 10% chance I come back. And if I'm 3 or more years lapsed, there's only about a 3% chance I come back. So what I'm really illustrating is this curve. If I'm 0 years lapsed, there's a high probability I come back. The longer I've been inactive, the less likely I am to come back. So if we think about how we're going to answer this, I would take the number of customers times my transition matrix times the value vector. This will be the forecast for 1 year out plus n transpose p squared times v. This is going to be the forecast 2 years into the future. And this should give me my answer. Now, what we can do is a little bit of math on this. I can pull the n transpose out 4, pull the v out on the other side, and we're left with this expression. So this would be the answer, $434,000. So if we go look at our histogram again, that would put us about here, $433,000. We're not the top entry, but we beat most of the other entries with an extremely simple Markov chain recency model. Now, just for fun, suppose that we wanted to find customer equity using d equal to 0.1. So just as a little review, we would need to use this formula. So let's go find that thing in the middle. If I take diagonal 4, that gives me an identity matrix, minus p over 1.1 gives me this whole thing. Now we need to solve it. So let's go solve it. We've inverted it. And then if I take, here's my initial vector transposed, times that, times the value vector, we'd have the total customer equity of that cohort from 2006 on. So it's about just under $2 million. In my next video, I will show you a few other applications of the migration model.